Welcome to this introduction on composite materials. In this short talk, we're going to highlight a number of things such as the types of composites, typical uses of composites, and how they can help us within the design process and the designing of new products. So let's explore in more detail together. So first of all, what are composite materials? Well, composite materials are a material that usually contains two or more phases, i.e. a multiple phase. And this often allows the material to exhibit properties that are usually unobtainable with a single homogeneous substance or material. So typically a composite material involves combining the geometric arrangement of a material as well as considering the high modulus and strength with a material of a lower modulus, but with a lot greater elongation at break. So some typical examples of composite materials are carbon fiber, glass reinforced plastic, amongst others. But interestingly, composites are also seen in the natural environment. So for example, tissues of plants and woods are typically a mixture of cellulose and lignin. And as a result of that, we see the natural combination of materials to create a natural composite. But also we get some less common and obviously non-natural composite materials where we combine a number of different elements. So for example, glass reinforced plastics, reinforced concrete with a metallic structure are classified as composite materials. So particularly important are composites produced from man-made materials that allow us to design products and buildings and infrastructure that allow that combination of maybe polymers and metals or concrete and metals and so on and so forth. So some great examples are laminated safety glass. So that's a combination of polymer and glass. Maybe a rubber cord, for example, that is the combination of rubber and fibers. Plywood, which is a polymetric adhesive and wood. And also fiber reinforced resin, so combining glass and other fibers together to create a thermosetting resin. So how do we categorize composites? Well, composites can be categorized into three main areas: particle reinforced composites, fiber reinforced composites, and structural composites. And within that, they have a number of subsections, but what we need to do now is explore composites and the history of composites in a little bit more detail. So let's have a look at a video that explains this really clearly.
What technology from prehistoric times is still behind some of our greatest innovations today? Composite materials. A composite consists of two or more distinct materials that combine to form a new material that is stronger than either of the components would be on their own. Composites are used to build everything from houses to aircraft. By combining multiple components into one supermaterial, previously impossible ideas have become possible. Forging a matrix, like cement, with a reinforcement, like steel rebar, creates a composite material strong enough for today's bridge decking. Let's take a look at some of the early forms of composites to see how we have created the precise and powerful materials we use today. Starting in 7000 BCE, humans began to use air-dried brick, a composite of mud and clay or straw, and wattle and daub, a lattice made of brushwood, reinforced by a sticky daub of soil, clay, dung, or fibers. In 3400 BCE, the Mesopotamians strengthened wood materials by gluing wood strips together at different angles, creating the first plywood. Ancient Egyptians used wood papyrus and plaster composites called cartonnage. And during the Han Dynasty, the Chinese composited paper pulp and adhesive to make the first papier-mâché structures. Concrete, still the most prevalent composite used today, was documented by ancient Roman engineer Vitruvius in 25 BCE. He created various versions of the composite using sand and lime cement. Much later, François Coinet ushered in the use of reinforced concrete with the construction of the first iron-reinforced concrete house in 1853. Reinforced concrete is a composite where concrete is combined with supports, such as metal rebar. In the early 1900s, American architect Julia Morgan created a 72-foot bell tower called El Campano in Oakland, California from reinforced concrete. This impressive structure survived the 1906 San Francisco earthquake with no damage, and reinforced concrete became widely used for its seismic performance and fire resistance. In 1905, Belgian chemist Leo Baekeland created the first fiber composite called Bakelite by combining plastic with wood flour or asbestos fibers. Heat-resistant and non-conductive, Bakelite was perfect for items such as kitchenware, electrical casings, toys, and records. Then, in 1936, DuPont released the first fiberglass by combining glass fibers with plastic, offering a material with a high strength-to-weight ratio that could replace wood and metal. Fiberglass became critical during World War II and was mass-produced for boats, ships, and fuselages, eventually leading into automobile production in the 1950s. The 1950s saw an explosion of fiberglass production for more diverse items like helicopter blades, printed circuit boards, and firearm components like lower receivers.
I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth.
But the space race of the 1960s demanded a material that was even lighter, stronger, and more heat-resistant. And the metal matrix composite, or MMC, was born. MMCs are composites of metal and another material such as ceramic. Carbon fiber, patented in 1959, and ceramic whiskers, developed in the 1960s, made composite materials more durable and suited to temperatures for aircraft carriers. The 1970s brought new inventions such as the Kevlar composite, using a nylon component called aramid. Kevlar is used heavily today for aerospace, automotive, consumer products, and environmental applications. As the space race continued, the need for temperature-resistant materials in space stations and shuttles increased. Composite developments in the 1970s were also driven by consumer markets, such as the automobile industry, and improved graphite composites began replacing wood and metal in sports equipment. Composites can be extremely useful for environmental preservation as well. In the 1980s, the production of the medium-density fiberboard composite provided relief from overlogging. In the 1990s, university researchers discovered how to remove chemicals and add polymers to make wood transparent, creating a shatterproof, biodegradable alternative to glass or plastic. While discovered in the 90s, transparent wood was never adopted, only now starting to be developed further. It's no wonder that by now, composites have transformed almost every aspect of daily life. As we continue to expand into space, biodevelopments, and alternate forms of energy, composites provide the basis of technologies we may have never imagined. Some of the latest composite developments include biometric hybrid composites that mimic the structural qualities of crustacean shells, spider web silk, or mother of pearl, the insulation properties of a termite mound, the self-healing properties of human skin, or the flight prowess of birds and bats. New nanocomposites, in which one part of the component is 100 nanometers or less, help in creating more powerful batteries, healing bones, creating flexible electronics, improving strength-to-weight ratios of materials, and identifying tumors in the human body. And robotic composites that combine sensors, computation, and actuating mechanisms allow materials to respond to different stimuli. Think of responsive camouflage or autonomous machines. Whatever the future may hold, one thing is certain: composites have been a critical technology since the beginning of human civilization and will continue to be the key monumental developments in our lives today. Who knows? Maybe composite materials are the secret to restoring our planet.
So why should we use composites? Well, composites provide unique benefits over traditional materials such as steels, aluminiums, wood and concrete. And this is down to the unique nature of the material and its ability to be adjusted to change the characteristics of the material in relation to the final product and how that final product will be used. So as a result of this, composites offer many advantages in terms of their physical properties, and this helps us in terms of our design flexibility too. So there are many benefits to composites, including them being typically lightweight, high strength, often corrosion resistant. They usually have good durability. Often they're non-magnetic, even though they may contain some metallic elements. They're usually easy to install, and there are various other reasons, as you can see, that are listed. However, the four key reasons why composites should be used and have some great advantages include composites typically have higher strength to weight ratio, composites are durable, composites open up many design options, and composites also are now a lot more easier to produce than they have historically been. So let's explore these in a little bit more detail. So why are composites useful when they have high strength to weight ratios? Well, perhaps one of their biggest advantages is that the fact that their high strength to weight ratio offers unique advantages. So let's take carbon fiber as an example. Carbon fiber typically is 25% as much as steel, but also 70% as much as aluminium. But it's typically stronger and stiffer than both materials. Also, when we think about high-end auto engineers, when they use composites, they're often used to kind of decrease vehicle weights by ultimately up to almost 60%. And that also helps in terms of improving crash safety and various other things, hence why it's often used in the motorsport industry. Composites being durable is also a massive advantage. They typically never rust, regardless of the environment. They often have less fracture toughness than metals, but more than polymers. But also there's a lot more dimensional stability. And why is that important? Well, that helps the composite hold its shape once it's been molded into position, regardless of whether it's hot or cold, wet or dry. So a lot of the time engineers choose composites over traditional materials to reduce the maintenance cost and also ensure long-term stability of the product. So for example, if you need a product to last decades, we should be looking at composites. Another reason composites opening up design options is the fact that it's sometimes hard to achieve things with traditional materials. So, for example, a single composite part can replace a full assembly of metal components. We can also alter the surface texture of composites a lot more easily. So there are lots of benefits within its ability to be used in a different design context. And finally, composites being easier to produce in this modern time is a lot more helpful to us as designers. So there are complex procedures in the past that have been made much more easier by things such as layout processes to help us fabricate composites. So the use of digital composite manufacturing has now helped a lot, and it's also sped up the manufacturing times, but also allowed us to tailor materials to those specific needs of the product. There are many examples of composite materials, none more so than glass fiber reinforced concrete, which many of us interact with on a daily basis. There is also carbon fiber reinforced polymers, plywoods, engineered bamboos, many of which are composite materials due to the combination of multiple materials together. So let's have a look at one of the most common composite materials that many of us interact with on a daily basis and how it's been manufactured in the form of carbon fiber.
Carbon fiber is an engineer's dream. Lightweight, yet incredibly strong. It's a string with thousands of parallel filaments. Multiple strings can be twisted into yarns, woven into fabrics, or molded with resin to produce materials called carbon fiber composites. Carbon fiber is 5 times stronger than steel, yet less than half the weight. To make it, they take a plastic fiber composed of thousands of filaments, far thinner than human hair. They then chemically alter it to form a perfect chain of carbon atoms for the final product. This mammoth machine lines up dozens of those fibers, which then travel through an oxidation oven for a couple of minutes. The oven temperature, about 480 degrees Fahrenheit, prompts the fibers to pick up oxygen molecules from the air. This rearranges the fiber's atomic structure, rendering them resistant to high heat. As the fibers oxidize, they change color to eventually turn black. They're now primed for the next process, carbonization. Furnaces heat the fibers in an oxygen-free gas mixture. This expels the non-carbon atoms and transforms the remaining carbon atoms into tightly bonded crystals, running parallel to the length of the fiber. This gives the fiber its strength. The exiting fibers travel through a bath of electrically charged water that etches the fiber's surface, so they'll better absorb resin. The next station applies a light preliminary coat of resin. This will strengthen the fiber's chemical bond to the molding resin. A spooling machine winds each fiber, now referred to as a carbon fiber toe, onto a bobbin, which buyers either weave into a carbon fiber fabric or mix with resin to mold a product. Another form of carbon fiber is pre-preg, sheets of resin-impregnated carbon fiber ready for molding. It's like ready-to-bake cake mix. The resin is a formula of epoxy and various powdered hardeners and accelerators. Workers pour the resin into a filming machine, which spreads it in a thin, wet layer onto paper. The paper is pre-treated with a release agent to prevent the final product from sticking, like spraying a baking pan with non-stick coating. Another machine, meanwhile, groups 200 to 300 carbon fiber toes into a giant band of fibers called a web. The width and thickness of the web determines the width and thickness of the pre-preg sheet. Workers mount 2 rolls of resin-coated paper onto the resin impregnation machine. A heating element warms up the web as it enters to facilitate resin absorption. Then, the heated carbon fiber web is sandwiched between 2 sheets of resin-coated paper. High-pressure heated rollers thin out the resin, so it penetrates the millions of carbon fiber filaments. Cooling plates then turn the liquid resin to gel, so that the next station can remove the paper, which pulls off easily thanks to the release agent. The next station covers the top of the pre-preg sheet with polyester film. This prevents the pre-preg sheet from sticking to itself at the end of the line, when it's wound into a roll like a fruit roll-up. In the factory's lab, technicians run quality control tests on pre-preg samples. First, they weigh the sample. Then they wash off the resin with chemicals and weigh the sample again. This verifies whether the ratio of carbon fiber to resin is correct. The lab also analyzes samples of composite, carbon fiber reinforced resin. In this tensile strength test, the computer measures how much strain the sample withstands before breaking. Such testing ensures the carbon fiber delivers optimum strength, durability, and heat resistance, whether it's used to make an auto part, a wind turbine blade, or a golf club.
There are also many other examples of composite materials, such as papier-mâché, engineered woods, composite honeycomb structures, and also fiberglass. Many of us interact with fiberglass on a daily basis as well. Fiberglass is often used for the structural profiles, for raised flooring, and many other applications. And finally, the last thing to consider is processes. For the creation of composite materials and composite products, there are many processes that we can consider. These can be either manual, semi-automatic, or automatic. Some of the common manual processes include hand layup, spray up, vacuum bagging, pressure bagging, autoclave molding. Some of the semi-automatic processes include resin injection, transfer molding, hot press molding, amongst others. And finally, the automatic processes include things such as filament winding, centrifugal casting, pultrusion, and in some cases, injection molding. If you want more information on composite materials and how composites are constructed, manufactured, and how their material properties are altered due to the material composition, please have a look at some of these useful resources. A number of the websites and demonstrations and videos that are available at these websites demonstrate how composite materials are manufactured, whilst also considering the material properties. Some of the examples that will be shown in the following videos in the other composite-based sessions will give you some examples on how composites can be utilized in real-life products. I hope you found this information useful, and please do have a look at the Future of Manufacturing TED Talk, as this gives you some really in-depth information about where composite materials could potentially take us in the years to come. Thank you for listening.